Okay, in the last video we introduced the tree diagram. This one's just going to continue to go through the examples from this lesson. So again, I'm on page 53 of the notes. So in this example, bag A contains 3 red and 2 yellow tickets. Bag B contains 1 red and 4 yellow tickets. A bag is randomly selected by tossing a coin, where head designates bag A and tails designates bag B. After the bag is selected, a ticket is drawn. So the first thing that's happening is that we have to choose a bag. Either we're going to draw from bag A or we're going to draw from bag B. And remember, bag A, we're going to draw from if we flip our coin and get a head, and bag B if we end up with a tails. Now I'm writing that because that helps me with this probability. So if I'm using a coin, there are 2 sides on the coin, and it's a 50% probability of choosing bag A, or in other words, 1/2. Same thing with bag B. Once we choose a bag, it looks like we then draw a ticket. So in bag A, we look back up at the information given. Bag A contains 3 red and 2 yellow tickets. So we're going to have red tickets and yellow tickets. And notice the probability there. There's a total of 5 tickets. 3 of them are red. So 3 out of 5 is the chance that I choose a red. And the 2 out of 5 is yellow. So we want to make sure it's probability listed on that branch, not just the number of tickets. Then the next one, if we look at bag B's contents, it has 1 red and it has 4 yellow. So again, the choices are red and yellow, and it looks like it also has 5 tickets. 1 of them is red, 4 of them are yellow. Determine the probability the ticket drawn is yellow. So again, we look at all the branches that take us to yellow. It looks like if we draw from bag A, we could get a yellow here. So we start with the probability the ticket is yellow, right? The first outcome would be possible from bag A. So we're going to say 1/2. Go down that branch to 2/5. Or we could draw from bag B and get a yellow. So that takes us down that bottom branch. So 1/2 times 4/5. So we go ahead and multiply that. We should end up with 0.6, or you could write 60%. The next example, you are off to play soccer and love being the goalkeeper. The likelihood that you will be able to play goalkeeper depends on the coach that day. Sam is the coach for 6 out of every 10 games, and when he coaches, the probability of your being goalkeeper is 0.67. When Alex coaches, the probability you'll play goalkeeper is 0.45. So first of all, the tree diagram, depending on goalkeeper or not, is determined first by the coach that's there. So either Sam is there or Alex is there as your coach. So when Sam is there, 6 out of every 10 games, so 6 out of 10, that means Alex is there for the rest of the games. So we would say 4 out of 10. That takes care of all 10 games. If Sam is there, it says the probability you get to be goalkeeper is 0.67. So that means that not goalkeeper is the rest of the time, right? Or remember, we do 1 minus 0.67, which would be 0.33. So that takes care of when Sam's the coach. When Alex is the coach, the probability of your being goalkeeper is only 0.45. Which means not goalkeeper when Alex is there. Oops, I put the word goal. Is 1 minus the 0.45. Or in other words, if that's 45% of the time, then you don't play goalkeeper the other 55% of the time. Calculate the probability you get to play goalkeeper. So again, if I get to play goalkeeper, I have to look at all the branches that would take me to goalkeeper. So it looks like if Sam's there, I get to play goalkeeper on this branch. So we would do 6/10 or 0.6 times 0.67. Or Alex is there and I get to play goalkeeper this amount of time. So go down that branch, we have 4/10 and 0.45. Multiply that together, we end up with 0.582, so about 58 0.2% of the time. Okay, last one, let's look at one that's drawing without replacement. So this says there's only red M&Ms and green M&Ms in the snack size bag. There's 5 red and 7 green. Dwayne takes at random an M&M from the bag and eats it before grabbing another one. Complete the following tree diagram that represents the situation. So again, every draw is its own set of branches. So this is like draw number 1. He reaches in and he grabs, and there's 5 out of the 12 that are red, which means the rest of them, right, 7 out of 12 would be green. So we're going to add 7 over 12 to this branch. Once he's drawn once, he's going to draw again. Now you'll notice if he eats a red, there's now only 4 red out of the 11 M&Ms that are left, right? If we think about how many green ones, if we're going down this branch, he didn't eat a green one, so there's still 7 out of the 11 that are left. So notice that accounts for all 11 that are left in the bag. If we go down the green branch, then notice it's like he chose a green and ate a green. So in this case, there's going to be 1 less green and 1 less M&M total. And the red, there's still 5 because we're going down the green branch. So notice kind of how that works. When there's not replacement, you just have to consider what happened here, and that changes a little bit of the possible outcomes going down each branch. So what is the probability Dwayne's first 2 M&Ms are both red? That would be this branch right here, red, red. So we're finding the probability that he gets red and red on his 2 draws. So 5/12 takes us down that red and red, and we can calculate that. What is the probability Dwayne chooses one of each color? So again, this one kind of has 2 different ones. It could be red and then green. Or, and remember when we say or, it's a new branch, it could be green and then red. So red and then green, that would be here to here. So we're going to do those ones multiplied. Or green to red, so then we'll multiply those ones. So red to green, or we're going to go green to red. And then we go ahead and multiply that out. So pretty high likelihood, right, that he gets one of each color. Lastly, what's the probability that Dwayne eats all the red M&Ms before getting a green? So this isn't all on our tree diagram, but if you think about this, if he's going to get all red M&Ms, that means a red, a red, a red, a red. So if he gets a red on the first one, that is on our tree diagram, we can see that 5/12. Then if the next one would be red, that would be 4 out of 11. And then if you think about it, now he's eaten 2 reds, so there's only 3 left out of the 10 M&Ms that are left. And then 2 out of 9 and 1 out of 9. And if we were calculating the outcome, we would go ahead and multiply that. And you can imagine getting all those red ones first is going to be a pretty small probability there. Let's see if I can calculate it real quick. So it looks like, you guys can see if you get the same thing as me, but a very small likelihood. So we're looking at something like that. Or it says 1 out of 891. We could write it as a fraction. So about 0.1% or 1 out of 891.